All right, so I got a couple of requests this morning. So I can back this up just a little bit. First was to explain what was going on with the Grenier Lab last week. So with the Grenier Lab, this is Orgo 2. The reaction we were hoping to run was this reaction. So we've got our benzene with bromine, and we add magnesium, which you etched with the HCl because originally it was covered magnesium oxide. You had the HCl that bubbles, and that gives you the exposed silvery magnesium. And you were supposed to reflux this in ether. Well, supposed to, you did reflux this in diethyl ether. And this was the ideal reaction here, was that you were going to form the Grignard, the magnesium bromide. And then subsequently, with the magnesium bromide and carbon dioxide, you were going to get a reaction that on an acid workup, so we're going to run this first in diethyl ether, and second we're going to add some HCl. This would have given you the desired benzoic acid. So this is what was supposed to happen when you ran the reaction. But here's the thing, the boiling point of diethyl ether here is about 50 degrees C. And as far as I can tell, this reaction doesn't occur at temperatures less than 150 degrees C. So all you did for that hour of reflux is basically heat this, this, and this. So this reaction never occurred. Basically, when you finish, you got the bromobenzene and the magnesium and the diethyl ether. And when you add the CO2, it didn't do anything because there was nothing for it to bind to. The most you got was probably some magnesium oxide reacting to form magnesium carbonate. Now, how do I know this is what happened? Well, this is a liquid, and this is a solid. So if you had recovered benzoic acid, you would have had a white crystalline solid when you got done doing the ether extraction. When you finished, the only thing you had left was a liquid, and it smelled just like the bromobenzene because that's what it was. It was the bromobenzene. So in terms of discussing what happened in your lab report, basically you did a very good job of refluxing bromobenzene with diethyl ether, and nothing happened. Big thing being because the temperature of the reaction couldn't get high enough. You can't beat the boiling point of your solvent. In this case, it's 50 degrees C. So probably what I'm going to look at this summer is switching to something like tetrahydrofuran. I looked at methyl tert-butyl ether, MTBE. I tried running that. Didn't get any reaction. Next thing I'm going to do is order some THF. Tetrahydrofuran boils about 168, 170 degrees C. Maybe that will give me the temperature I need, and then the only other option there is to basically just reflux in bromobenzene and then try some extraction methods to pull it out that way. But ultimately, you couldn't make what you need to make because you couldn't get the temperatures high enough, and this is kind of the double-edged sword. Grignard reagents typically are pyrophorics. They burn spontaneously in the presence of air, so we need to make a Grignard that is stable enough that can be done without you having to do this with air-free techniques, because we just don't have the equipment to do an air-free technique. This means we end up generating a Grignard that's super stubborn to make, which is why it's super stubborn to react. Now, the other question I got asked was about the Organic 1 exam, and where's my eraser? There you are. It concerned one of the stereochemistry problems. So you're given this molecule where you've got 3 methyl groups, 1, 2, 4 trimethyl cyclohexane, and you're asked what is the most stable geometric conformation. So basically, what does it look like? Number of axial and equatorials. Now, what's going to guide us here is we want to maximize the number of equatorial bonds, but here's the thing, the cis-trans is going to dictate how they are relative to each other. So for me, the easiest way to do this is to build your cyclohexane and crush it down so it's in the planar conformation, and then build up this molecule. So this is that molecule up there. And I'm going to take it, bend it into the boat conformation. What I get is 1 axial and 2 equatorial. Now, if I bent it another way where I ended up with 2 axial and 1 equatorial, I would know that really the only thing I'm using this model to do is figure out how many groups are in the same positions versus opposite positions. So I have 2 there in the same position, 1 in the opposite position. So I want to bend this in such a way that I maximize the number of equatorial groups. So the answer to this would be 1 where there is 1 equatorial, or 1 where there is 1 axial, and the other 2 are equatorial. Now, what's another way of doing this modeling kit? Well, the other way is that you build the structure, or you draw the structure, and you have to remember that when groups are adjacent, or they're 3 carbons away. So let's start, this is our reference carbon. So because these are cis, they're going to have opposite positions. So if one's axial and one's equatorial, and this is true for any atom that is 1 or 3 carbons away. So let's say this is just plus, these are going to end up being minus, and we're going to use plus and minus to describe axial or equatorial. So if one is axial, the other is equatorial. We want to maximize the number of equatorial bonds, so since these two are going to be the same, we'd want both of these to be equatorial, and that makes this one axial. And that's how you do that problem. Now, the thing to keep in mind is that axial and equatorial, everything wants to be equatorial. That cis-trans is going to dictate whether or not they're axial or equatorial relative to one another, whether or not the same orientation or not. So ideally, you'd have all 3 in the equatorial position, but that would require this one to be trans to these 2. And that's really all the questions I got in advance. Any questions out there in the chat? Does everyone have a lab worksheet submission for the TLS lab? If so, I do not see it on Blackboard. So it should be up there. Let me check. Yeah, there has to be because I saw a lot of people with it in lab. How odd. It's there. The release date's off. No way, it says... What? So if you take a look at the course website now, you should be able to see it. And I need to update the schedule for the. It looks like for your shell, I got shifted on the assignment due dates. Yeah, you should be able to see it now. Yeah, same question as his. You should be able to see it now. But let me check to make sure it's not an issue with both shells. Oh, how weird. I guess we moved the lab schedule. Yeah, you should be able to see it now. You're welcome. Yeah, it looks like when I was setting up the Blackboard shell, I got February, March flipped up because suddenly it goes from like March due dates back to March due dates. Okay. Change that too. Wow, we're coming up on spring break soon. Awesome. Oh, I apparently got time on my hands. Explain first degree, secondary alcohols, and tertiary alcohols. So they're going to follow the same line. Basically, they're described by the alcohol, by the carbons they're attached to. So if we had just this generic molecule, and we said, what are the different carbons? We would say this is a primary carbon, secondary carbon, and tertiary carbon, and each of these are also primary carbons. Alcohols, it's defined by what carbon they're attached to. So if you have an OH here, this is a primary alcohol. OH here, this is a secondary alcohol. OH here, this is a tertiary alcohol. And the degrees here, first degree, second degree, third degree. Hey, you're welcome. TLC worksheet. So when you run a TLC plate and you run a worksheet for a lab that has a TLC plate, the thing is people don't necessarily do things in the same order in which you would do them. So I personally like to put my unknown at the very right side and then put all the references on the left. Some people prefer to do the reverse, like put the reference, or sometimes people like chaos and they don't really organize the top. So if you look at the worksheet, let's say we have 3 channels. So the way the worksheet is set up is it gives you a channel. And then it gives you spot 1, 2, 3, 4, so forth, and it goes to the next channel. And then it asks you for the name, the distance, and then the calculated RF. So let's say you actually know what the spot is. So let's say we have so we've got channel 1, channel 2, and channel 2. And let's say channel 1 is my reference and it contains acetyl salicylic acid. Well, I would say that spot 1 is acetyl salicylic acid. And then I would measure the distance here, D, record at the distance, so let's say that's 1.4 centimeters, and our RF is 0.25. Now, let's say channel 2 here is my unknown, and I've actually got multiple spots. and I don't know what they are. So I've got spot 1, but I'm not going to have any names because I don't know what they are. So I'm just going to leave that blank. So for references, we know what the spot is because there should only be one thing in that channel. And I record my different distances. So let's say it ends up being 0.1 or 0.5, 1.4, 2.3, 3.3. And then I do my retention factors. So let's say that's 0.1, 0.25, 0.38, 0.49, just arbitrary numbers. So this worksheet is set up so this way you can organize these spots however you want to. The channels here, so you got your TLC plate and then the solvent mixture, because that's what you're varying here. The different channels correspond to the different channels that you set up for running your TLC. The spot refers to any spots along that channel. Now, for references, you should only have one, and you should be able to tell me what it is because you spotted references. But for something like an unknown, you're going to have multiple spots because it's a mixture of things. So you're not going to know the name. And then the distances, just how far it traveled from the start point, and then your RF, you're going to see there's a solvent entry. And the solvent distance traveled is from the front start line to the finish line. It's every single one of these distances divided by however far the solvent traveled. Screen is kind of blurry. I think this is more of an issue of the bit rate. So let's say you got your channel. So channel 1, you would only have one spot. You would label it. Let's say channel 2 is your unknown. In that case, you're going to have multiple spots. You don't know what they are, but you are going to have to list their distances and their retention factor based on the solvent. But if you look at it, each page is a TLC plate. So page 1 is TLC plate with a certain solvent mixture. Page 2 is a solvent plate with a certain mixture. Page 3 is a TLC plate with a different mixture. And you basically have a lot more rows than you actually need to fill that out. So don't think that there's supposed to be something in every single row. It depends on how you set up your TLC plate, which will dictate how you fill in, like how many spots there were, what their different travel distances were, and what the retention factors were, and if you knew their identities. You're welcome. So in the TLC, you have 5 channels, but the number of spots depends on what you're running. Typically with a reference, you're only going to want to have one spot, but your unknown, as it's a mixture, will definitely have more than one spot. Question 14 on the test material for the Orgo 1 homework. All right, let me bring it up. Name the following compound according to the IUPAC nomenclature. Oh, this is a hateful little one. So the OH is not attached to the second carbon. It's attached to the first carbon. And the reason we do this is alcohol is the most reactive group. So what we want to do is make it the one that sets all the numbering. So we got an ethyl chain, and this is an ethanol. See, it's going to make you do the number in the center. Alcohol is going to set the chain. We have a methyl and a cyclopentyl. So there should be one methyl, one cyclopentyl, one ethanol. That's curious. That's not how I would name it. Oh, okay, that's an interesting way to do it. Go them. So what they're defining as the longest branch is the propyl. So it's 2-propanol, and it's 2-cyclopentyl. I guess that makes sense. That reduces the complexity of the molecule. So let me try it again. It's I've got 2-cyclopentyl, 2-prop, no. So yeah, if you put the second position for the alcohol, it should work. Shall I show you my desktop? So if I do 2 and 2, cyclopentyl, prop, and all. This is question 14. Saying it's correct. So it's accepting the 2 on my end. You're welcome. All right, so that's in the live stream today. For the Orgo 2 folks that are checking in, make sure you remember your exam is opened up yesterday morning, so you have until Sunday to complete the Organic 2 exam. Otherwise, I will see you all later this week. Thanks for coming.